We've explored how generative models create images by reversing a noise process, but denoising diffusion probabilistic models, or DDPMs, took this idea to a whole new level.
This paper from Ho et al. In 2020 really cemented diffusion models as a powerful contender for high-quality image synthesis results.
Denoising diffusion probabilistic models are a specific class of latent variable models. They essentially learn to undo a known gradual corruption process.
So it's about systematically cleaning up a noisy signal rather than just generating from scratch? That's quite a shift from typical generative approaches.
Yes, it's about reversing entropy, similar to considerations from non-equilibrium thermodynamics. Think of it like reversing the mixing of two gases. You start with a mixed state and try to unmix them.
That's a fascinating analogy. So the latent variable aspect refers to the noisy intermediate states?
Precisely. And this approach led to remarkable benchmarks. For instance, on CFAR-10, they achieved an inception score of 9.46 and a state-of-the-art FID score of 3.17.
State-of-the-art FID score means the generated images were incredibly close to real ones, right? That's a huge leap for diffusion models. We've seen diffusion models before in #TCM003005. But what made this specific work by Ho et al. So impactful? What was the conceptual breakthrough that led to such scores?
The key was a novel way to frame the learning problem. It's not just remove noise, but predict the noise itself.
The authors found a novel connection between diffusion probabilistic models and denoising score matching. This allowed them to design an objective function that was surprisingly simple yet powerful.
Denoising score matching sounds complex. Does it mean the model learns the gradient of the log probability of the data?
Exactly. This connection enabled training on a weighted variational bound designed according to a novel connection. It made the previously intractable problem of learning the reverse process solvable.
So they found a tractable way to optimize the model, turning a difficult probabilistic inference into a more straightforward denoising task?
The result was tangible. Sample quality similar to progressive GAN, which was a leading generative model at the time. This showed diffusion wasn't just a theoretical curiosity anymore.
That's a strong statement. It means they were generating images that looked as good as those from the best contemporary methods, but with a different underlying principle.
This approach also naturally permits a progressive lossy decompression scheme. The model generates images from noise, gradually adding detail, which is visually quite appealing.
It sounds like an image slowly coming into focus. So you can see the image forming step by step during generation?
You can indeed. To truly grasp how it works, we need to understand the fundamental forward and reverse processes. Let's build that intuition step by step.
Right. How do we actually add and remove noise in a structured, learnable way?
Let's start with, what is a diffusion model? At its core, it's about transforming noise into data and data into noise.
So it's a two-way street where one direction is predefined and the other is learned?
Correct. We begin with a fixed, or predefined, forward diffusion process. Imagine an image slowly dissolving into static. We add a tiny bit of Gaussian noise repeatedly.
Like repeatedly blurring a photograph, but with random static, not just a smooth blur.
Exactly. This process gradually adds Gaussian noise to an image until you end up with pure noise. We control exactly how much noise is added at each step using a variance schedule.
So this is not random. It's a precisely controlled step-by-step corruption to ensure it ends up as pure Gaussian noise?
So the forward process is always deterministic in terms of its parameters, like the noise schedule. The randomness only comes from the Gaussian samples.
That's right. The schedule of how much noise is added is fixed and known. It's the starting point for training.
Now for the learned reverse denoising diffusion process. If we think of the forward process as making soup, the reverse is unmaking it, separating ingredients.
That's a good analogy. It's much harder to unmix than to mix. We need a recipe for the unmixing.
This recipe is a neural network that is trained to gradually denoise an image starting from pure noise. It learns to reverse the blurring and static addition step by step.
So it's essentially learning to perform the opposite of the fixed forward process, but in reverse order. But if the forward process just adds random Gaussian noise, how does the network know which noise to remove at each step? It doesn't have the original noise.
That's the crucial insight. The network isn't trying to subtract the exact noise that was added. It's learning to predict pure Gaussian noise that should be removed to make the image slightly cleaner. This builds on our TCM 003005 case. Diffusion models are a kind of generative model that convert noise from some simple distribution to a data sample.
So DDPMs are a specific effective method for performing that noise to data conversion we discussed previously.
Ultimately, the goal remains the same for many generative models: to convert noise from some simple distribution to a data sample. DDPMs achieve this through this denoising dance.
It's like guiding random static into a recognizable image, one small denoising step at a time. That feels much more manageable than generating an image all at once.
Exactly. But how does this neural network actually learn to predict the noise? We need a mathematically tractable way to train it. How do we turn that intuitive idea into an actual loss function the model can optimize?
The core problem in learning the reverse process is that we don't know the exact conditional distribution of the previous, cleaner image given the current noisy one. It's intractable.
Intractable because it depends on understanding the distribution of all images, which is impossible to model directly?
Precisely. So we leverage a neural network to approximate or learn this conditional probability distribution. This network will guide our reverse steps.
We're using the network to infer the most likely less noisy state given the current one.
And here's a crucial design choice. The DDPM authors decided to keep the variance fixed and let the neural network only learn the mean of this reverse Gaussian distribution.
They simplified the problem, so the network isn't predicting how spread out the noise should be, just where the center of the clean signal is. My intuition wants the network to predict the clean image. Is it just a complex image denoiser?
That's a common pitfall. The elegant trick is that the neural network becomes a noise predictor rather than a direct mean predictor. This is more stable.
A nice property of Gaussian noise allows us to sample at any arbitrary noise level conditioned on the original image without iteratively applying the forward process.
So for training, we don't have to run the forward process many times. We can directly jump to any noisy state xt from x naught. That saves a lot of computation.
Exactly. This property, combined with some math, lets us instead reparameterize the mean to make the neural network predict the added noise.
So the network predicts what noise was added to get to the current noisy image, not what the clean image should be. That's a subtle but important distinction.
Imagine we have an image. Add random noise to it. The network sees the noisy image and a timestamp, and its job is to guess that exact random noise we added.
So if the network predicts the noise perfectly, we can just subtract it from the noisy image to get closer to the original?
That's the idea. The final objective function is a simple mean-squared error, MSE, between the true and the predicted Gaussian noise. It's beautifully straightforward.
So all that complex probabilistic theory boils down to a familiar MSE loss, but on the noise component, that's very elegant.
For the neural network itself, the DDPM authors chose a UNet, introduced by Ronberger et al. 2015. It's highly effective for image-to-image tasks.
I remember UNets from image segmentation. The encoder-decoder structure with skip connections seems perfect for processing images at different resolutions.
Yes, the residual connections between the encoder and decoder are key. They help preserve fine-grained details during the downsampling and upsampling process.
So the UNet helps ensure the network can both grasp the overall image structure and predict precise pixel-level noise.
We've seen how DDPMs produce excellent samples by learning to predict noise, but the original models still had practical limitations.
Was it mostly about how long they took to generate images, or the computational cost?
So what exactly did Dhariwal and Nichols' improved DDPMs tackle?
They showed that with a few modifications, DDPMs could achieve competitive log likelihoods while maintaining high sample quality. This meant they were even more robust.
A major improvement was learning variances of the reverse diffusion process. Remember, the original DDPMs kept this fixed.
Oh, so instead of assuming the variance, the model now predicts it, giving it more control over the denoising step?
Exactly. Imagine trying to hit a target. If you know not just the direction, mean, but also how spread out your shots usually are, variance, you can adjust your aim more precisely.
So each denoising step becomes more informed and efficient, requiring fewer steps overall to reach a clean image?
This precision directly translated to efficiency, sampling with an order of magnitude fewer forward passes. This means generating images much faster.
That's a huge practical win. Slow sampling was a common critique of early diffusion models.
The best part? This speed-up came with a negligible difference in sample quality. You got the speed without sacrificing visual fidelity.
So the improvements weren't just theoretical, they made DDPMs genuinely more usable in real-world scenarios.
This efficiency is important for the practical deployment of these models. Faster generation means they can be used in more interactive applications.
This is what helps push research ideas into actual products and services, making them viable outside of a lab setting.
Furthermore, they found that sample quality and likelihood of these models scale smoothly with model capacity and training compute.
This is excellent news for scaling up. It means throwing more compute and a larger model at the problem reliably yields better results. No hitting cliffs.
They also used metrics like precision and recall to compare how well DDPMs and GANs cover the target distribution. This showed DDPMs could learn the full diversity of data better.
So DDPMs weren't just generating beautiful images, but a wider variety of beautiful images, capturing the full dataset richness?
Absolutely. These improvements made DDPMs a dominant force. The idea of learning to predict noise, rather than directly reconstructing an image, became a cornerstone.
This framework allows for incredible quality and is continuously being refined for speed. I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.